Hi everyone. I'm going to do a quick video on gear ratio. Now, it sounds all complicated and everything, and it's really not, but it's certainly a valuable thing that you could use in your build to your advantage, whether it's to increase the rotational speed of a shaft or decrease that and increase the torque in that instance. But so I made this little device right here. It's really nothing more than like a visual aid to actually run the motor and see the different speeds that are generated by the gear ratios that we have. And these three outer gears right here are representative of the gears that are available to us are these right here. These are spur gears, the most common gear. They're made to operate in the same plane like this on two parallel shafts. Like if these two were connected, or the center shaft and this shaft and around that. That's how these gears are designed. They have a straight cut tooth on them, and they're just made to mesh that way. So we'll get to this in a minute, but let's look at how to calculate the gear ratio first. It's very simple. You need to identify how many teeth are in the gear. And for us, in this case, our larger gear is 36 teeth. And if it was paired with our second largest one right here, our second largest gear, that has 24 teeth. So it's really as simple as 36 divided by 24, and that would give you a gear ratio of 1.5. And what that means is for every time the larger gear travels 360 degrees, the smaller gear is going to travel 1.5 times that. So as you could see in this instance, if these two were paired and this was what they call the driven gear, or the input gear in some cases in engineering, this would be the gear attached to the motor itself. And so the motor has a specific RPM, and that's what this gear would be traveling at. Well, attached to this one would be traveling rotationally 1.5 times faster than whatever the input speed of the this particular gear is. And that holds true for, the smaller gear too. You would do this math right here. So this happens to be the 12th tooth, so it'd be 36 divided by the 12, and that would give you a gear ratio of 3. So this would be traveling 3 times as fast as this one rotationally. If this were the input gear, in other words, the smaller one were attached to the motor and driving this larger gear, you would decrease the rotational speed of the larger gear, but you would increase the torque. So if you had the need to maybe lift something heavy or whatever, you may want to reduce the speed but increase the torque on that particular gear. So the configuration will give you a different outcome. So another thing you can do with these gears, which is kind of interesting, and I just did a quick math formula thing here, you can create a gear train. Now, a gear train is more than 2 gears joined together. In this case, we have 3. So if this is the input, the gear that's driven by the motor, and this is the output gear, this is the one that's going to be driving something on your device, you need to know what the gear ratio would be between those. And it really is as simple as doing the gear ratio between gear A and gear B, and you come up with a number. And then do the gear ratio between the B gear and the C gear, and you would come up on another number. So as you see in the formula, it's A over B, B over C. So it's 36 divided by 24, and 24 by 12 gives you 1.5 and 2. And then you multiply those two together, those two findings, and you come up with 3. So the gear ratio between the driven, or the input gear, and the output gear, or in this case the smaller one, would be 3. Now, you'd get the same thing if you did that, though, too, right? But so why do we have a gear train? Well, in this case, if this is moving clockwise, that means the center gear is moving counterclockwise, which in turn makes this one move clockwise. So by putting that second gear, that essentially idler gear between the two, what you've done is you haven't changed what the gear ratio would be, but you changed the rotational direction, right? If this were just like this, you would have clockwise and counterclockwise. But if the desire is to have them both turning in the same direction, so that's what you've created there. So you'd have clockwise and clockwise. So that's just really touching on gear trains just lightly. So let's see what happens when I hook up the controller and my battery, and we'll see what we get. In my model here, what I have is the input gear is the central gear right here, the 36 tooth. And then if you notice, these 3 gears are only attached to the input gear in the center. They're not relative to each other at all. They're individual. The reason I did that, I didn't want them influencing each other, obviously, and I wanted you to get a visual as to how that is going to rotate and give you a different rotational speed. So let's hook this guy up, and you'll see. So as you can see, the input gear is moving at a constant, whatever the RPM based on the spec of the motor, and it's turning the smaller gear with the 3-to-1 ratio that it has much faster, obviously. So there you can use your gears to actually change the rotational speed of something, or increase the torque if it were the smaller gear is the input going to a larger gear. So that's kind of neat. The build itself is kind of fun. I mean, it really isn't specific to any challenge or whatnot, but I used 3 plates. I used the motor bracket plate right here with the standard motor, the output shaft of the motor right here going through to a bearing assembly that you can see where the shaft goes through. There's actually a ball bearing in there, and then bearings for each one of the driven shafts. And then I've got the E-clips holding the shafts onto the drive shaft itself, and then an acrylic plate here. And the acrylic plate does 2 things. Number one, gives you a visual as to what the gears are doing, and the other thing is it acts as a bushing plate also, so that it takes any load off of the shaft, like any of the pressure angle from the gear itself would cause this gear to want to push away. So if you're not supported on both sides of your gears, sometimes that can lead to problems. So this actually affords that also. So it's a multi-purpose plate. Plus keeps your fingers out of the gears. I know they're only plastic, but they can still chew you up pretty good. So these caps right here are just visual. They're just pressed onto the shafts, and these little roll pins right here just give it a better visual rather than have to look at a small radius going around in a circle. This gives you an idea. So it's kind of neat. And there's a lot of information in this particular build that could really be advantageous to your strategy, whether it's increasing the rotational speed of your drive wheels on your cart, or wrapping a spool up faster, or running a rack and pinion faster, or whatever the desire is, or whatever the application is. Using gears to get there is pretty fun. So that's about it for this one. Hopefully that helps.